In this lesson, we're going to take a look at some properties of circles relative to radians. Some of these ideas are old like grade 9. Some of these ideas are old like yesterday. And we got a couple of new ones. Just some terminology for us to start. I think you know most of these, but just in case, let's start with a radius. It's a line joining the center to any point on the circle, so OA or OB. A diameter, the line going through the center, touching both sides, so AB is the only diameter we have there. Our new one for this unit, arc, the curved exterior line of the circle between any 2 points. So obviously E to F, but it could be any points on the outside. Our formula is A equals theta R, which really is just the idea of circumference. Circumference of a circle is found by 2 pi r. But if we don't go all the way around the circle, when we go part of the way around the circle, that 2 pi becomes a portion of 2 pi, or what we call the central angle. That's our new one. The central angle is not the whole thing, it's just part of it. Some old ones from way back in grade 9. A chord is a line joining any 2 points on the circle, but not through the center. And a tangent, a line that makes 1 point of contact with the circle. What's nice about tangents is when they make that point of contact, they actually form a right angle. The idea of right angles is super handy to us because we can think about the idea of Pythagoras. Often when you start dealing with tangents, you can say to yourself, hey, there's a triangle, there's an A, a B, and a C, and I can start figuring out the lengths of different things, whether it's the radius, whether it's the tangent, some combination of those two things. As soon as I see the word tangent, I know it's a right angle. Okay, let's talk about some old ideas. Maybe pause the video, try these yourselves. You actually know how to do them. You just need to think about it a little bit. Calculate the length of each line segment, chord AB. Well, this first idea here is Pythagoras. Okay, I've got a side A, I've got a side B, I've got a side C. So how about 3 squared plus x squared is 5 squared. I'm thinking this is my x. And this one we can probably just do in our heads. 5 squared minus 3 squared is 16. Square root of 16 is 4, which makes AB 4 and 4, or in other words, 8 centimeters. Diameter AB, we can find any diameter if we know 2 chords that are attached to it, because they will always form a right triangle through the diameter. The reason there is this angle is 180, and you might remember from grade 9, way back when we had this property of circles, that if you take your central angle and the one that's formed in the corner, this is always half of that, making this guy always 90. If that's a 90, well, then we can use a squared plus b squared equals c squared, where c is your hypotenuse, or in this case, your diameter. Calculator-wise, you should get 625, or in other words, 25 centimeters for AB. Those are some old ideas way back when, how we can actually use some of these lines. You could probably also use tangents in a similar way, because Pythagoras will come into play there too. Let's talk a little bit about yesterday's idea. So arc length, how it's related to the central angle. Okay, in our diagram here, I want to find an arc length. We know arc length is always r times theta, that portion of the circle. Be careful that theta is in radians. This one's obviously not. This one's in degrees. But we can convert to radians by pi over 180. And you can think of that as 200 pi over 180. But we usually reduce that, and we'd say that's 10 pi over 9. So my radius is 10.2. I got 10 pi over 9. Multiply them together. And because I have decimals for my radius, let's use decimals for my answer. And how about 35.6 centimeters? That's the 3 sig figs. Use your pi button in there. Hey, you guys can try B. B is pretty nice. Looks to me like our central angle is already in radians, so you don't have to convert it. In fact, because this one doesn't have any decimals in it, you can actually leave this as an exact answer of 12 pi over 5, and you can be done with that. Just call that centimeters. If you really want to put in the 3 sig figs, you can call that 7.54 centimeters. So honestly, I'd just leave it as exact, 12 pi over 5. Okay, one last one for you guys to try. If you haven't paused yet, pause this one, give it a try. Find me x, which happens to be the radius in this case. Okay. Okay, in this case, we know our arc length. We don't know our radius. Our central angle, be careful, the central angle has to be the one opposite the arc. So I need that angle, which obviously is a circle, so what's left over is 100 degrees for that. But that's degrees, we need radians, so 100 times pi over 180. That's 100 pi over 180. We can reduce that to 5 pi over 9. Okay, that's my central angle. I want r though, so we're going to take 15 and divide it by 5 pi over 9. Okay. You can use your calculator, or if you want to do it by hand, flip the fraction. And we could say it's about, what's that, 27 over pi? That's exact. Decimal version, how about 8.59 centimeters for r? Let's go with centimeters, was it not? Yeah. Okay, those are the ideas from yesterday about arc lengths. Let's take a look at some new ideas. These new ideas deal with sections of circles. Okay? They're relative to our central angles. We still need that idea of radians, but now we're going to find the areas of things. The first area is called a segment. It's what happens when you connect an arc and a chord. That section of the course, or section of the circle, is called a segment. If, on the other hand, you have radii and a chord, so that would be this one over here. Radius and an arc. So there's my arc, there's my chords, there's my central angle, of course. We call this thing a sector. Okay, so one of those deals with central angle, one does not. But to get the area of a segment, we actually need to know the areas of sectors. So let's try a couple things here. First idea, in our formula booklet, the area of a sector is always 1/2 r squared theta. I do want to point out, really this is just a handy rearrangement of area of a circle, pi r squared. Okay. Pi r squared is the area of a circle. It's just we don't have the entire circle necessarily. We've got part of the central angle. So we think of that as I've got theta out of my 2 pi. That's my portion of the entire circle. I don't go all the way around. Maybe I stop there. So I've got a portion times r squared. And what can we, pi r squared. What can we do with the pi's? I can cancel them out. I've got my 1/2. I've got my theta. I've got my r squared. Or in other words, I've got this formula. Don't have to worry about the development, just worry about how to use it. Okay, I want to find the area of this sector. My formula is 1/2 r squared in whatever portion of the circle I have. Well, my r is 10.2. My central angle is 260. That's degrees, so pi over 180. And you can reduce that if you want to. What's that? 13 pi over 9. Or to be honest, you could just take this number and put it into your formula. It'll work. Your calculator can do all that one time for you. Use your pi button. It keeps it more exact. Don't have to worry about rounding. And you should get 236.06, which to 3 sig figs just rounds off to 236. Okay, that's how you find the area of a sector. It's a sector because this is the central angle. Okay, let's work it backwards. If I know the area, can I find the central angle? Well, of course we can. Let's take that same formula. We know our area. We know our radius is 4.8. We want to find our central angle. How much of the 2 pi have we gone around? So we're just going to take 51 and divide it by whatever 1/2 times 4.8 squared is. You can put that all in your calculator once. If you do, you probably need the brackets around that part. Or do the bottom part first and divide 51 by your answer. I got 4.427, or in other words, 4.43 to stick figs. It doesn't say it, but we know it should be radians. You don't have to say it. It's assumed that's a radian answer. And it's a decimal. It's not exact. That's okay. Okay, those are segments. Let's talk about, sorry, those are sectors. Let's talk about segments. Okay, that's I have a chord in my arc length, and obviously here's a chord, here's the arc length. I want the part in between that. Well, to do that, as I said previously a second ago, you actually have to find a sector first. You have to think of this as, well, let's find this entire piece of pi. So my sector is 1/2 r squared theta. R is 6. Theta is what's in radians already, which is kind of nice. And if you do that, you should get 37.699. But again, that's actually all of this. We don't want all of that. We want just the red part, which means we have to get rid of this part, which looks an awful lot to me like a triangle. You might even remember the area of a triangle can be given by the formula AB sine C over 2. These are two sides, any two sides. This is the angle between. So 6 times the sine of 2 pi over 3, all divided by 2. Now you can use your calculator to do this, just make sure it's in radians. If you do that, you get 15.588. And because we only really want the red part will be 37.699 minus 15.588, or in other words, 22.111, or 3 sig figs centimeters squared. And that's how you find the area of a section, or a segment, if you will. Okay, take your sector, subtract the triangle inside. It can be done for everyone. Okay, that's the end of the lesson. We're just going to do a practice sheet today. There's no textbook stuff on this. It's more of an IB topic. So try the sheet, answers there, check them. If you're stuck on something, come see me, send me a question. I'll help you out.